All right, Chapter 7, Work and Kinetic Energy. Question number 3. The inclined plane, right, is a simple machine that enables us to do work with the application of smaller force than otherwise necessary. The same statement applies to a wedge, a lever, a screw, a gear wheel, and set of pulleys, such as in sample problem 7-4. Far from saving us work, such machines in practice require that we do a little more work with them than without them. Why is it so? Why do we use such machines? Well, incline plane, or simply like a ramp, is the simplest machines that humans have invented. If you were to look at an inclined plane, and when humans were building these huge lapidarious structures to commemorate certain celestial events, or perhaps even human events, right? In order to lift a huge stone up on top of two columns, it would have taken an immense amount of manpower to actually lift that straight up and raise it higher than their height, of their human height, to place it on top of columns. However, if they were to construct a ramp, some people believe pyramids were built this way, using ramps. Okay. If there were no friction, but obviously there is, but only force they would have to overcome, to make it simple, let's say there is no friction, they would put these huge slab of stone on like sleds, and there were people who would pour water underneath the sled to make the friction less. So of course this is Fg, which is weight, which is equal to mg. This Fg is actually broken up into its components in the x and y direction. So here you have Fgy, right? And then you have your Fgx. And your Fgx happens to be, well, if this angle here were theta, this angle here is also your theta. Therefore, it is mg sine theta. Now, Fgy is mg cosine theta. So, in order to lift this from here to this height, right? This height right here, you don't have to literally use the same amount of force as the weight of this block. You just need to overcome this mg sine theta. So if you were to make this ramp really long and shallow, right, from way back here, let's say like this, right, this will go less and less, right? This will go less and less. So what you really need to do is you need to have F push that is going to be just bigger than Fgx, right? So F push, so this is F push, needs to be bigger than, right, or equal to, I guess, mg sine theta. Okay? Because once you got it moving, you don't need to. Okay? So if there were no friction, right? Right? If there were no friction, F push has to be greater than or equal to just mg sine theta. Okay? So you don't need to be really strong to lift this thing. You just need to be mg sine theta strong, right? So okay. So notice the normal force and FGY will not do any work because they are perpendicular to the delta x, right? And if you were to think about it, this is, I guess, the delta x. Okay. So if you were to think about work being done, work is equal to mg sine theta, right, times delta x, right, times cosine, right, of, I guess, if you want to, you want to have this F push is your mg sine theta, right? So this is your really your F push, right? And this will be 0 degrees. Okay? So since cosine of 0 degrees is 1, right? If you were to look at this, right, this is really nothing more than just delta x sine theta is just h. So this right here is h, right? Therefore, work is equal to mgh. But of course, in reality, there's always going to be friction involved, right? So you're going to have to add friction somehow into this work done. So you're going to have work done by friction as well as work done by Fg. All right. All right. So it seems like we're getting something out of nothing. Is that true? Well, less force we use, more distance we have to travel. So we're really not getting something out of nothing. We still have to do longer distance, right, to do same amount of work. So no matter how you look at it, whether you lift it straight up or traveled a long distance to get it up there, you're doing same amount of work, except if you're doing long distance, you don't have to use as much force to bring it to the same height. However, if you're going straight up, you have to use a tremendous amount of force to go short distance h. All right, so hopefully you can see that. All right. All right. Next. An overhead view of these three objects shown in three situations in which box is acted on by two forces, right, of equal magnitude. So these forces are all same value, right? This is the velocity vector, okay? So keep that in mind. As the box moves, the forces maintain their orientation relative to the velocity v. For each situation, determine whether the work done on the box by the net force during the motion is positive, negative, or zero. All right, so for part A, looks like if I were to add these two forces, they're going to produce a net force, right, going this direction. So here, for part A, right, since I have two forces going this way and this way, right, F and F, it looks like I'm going to produce a force, a net force, going this way. Right? Because these two horizontal components has to add up to this. These two vertical components will cancel each other out. However, the velocity vector is going this way, which means that is the same direction as my delta x. Therefore, since the angle between them is 90 degrees, right? So work done therefore work is equal to 0, right, joules, because of cosine of, right? So the net force times delta x times cosine of 90 degrees. This goes to 0. All right. So what about part B? For part B, you know the force is going this way, another force is going that way. So my net force is going to go this way, right? However, my delta x is also going this way, right? Because that's the velocity. Therefore, the angle between my f and delta x is 0 degrees. Therefore, work is positive. And for part C, well, I have two forces going this way, right? Therefore, I have my net force going this way. And since my velocity vector is going this way, that is my delta x vector as well, right? And because my velocity vector is delta x over delta t, velocity and delta x have same direction. Okay. Therefore, since the angle here is 180 degrees apart, right, my work is negative. All right. Any questions so far? All right. Now let's take a look at the next question. A greased pig has a choice of 3 frictionless slides. Okay. Wow. degrees pig. Brings me back memories at St. Joe's Prep. All right. Compare the slides according to how much work the pig's weight mg does on the pig during the descent. Okay. Well, it looks like the height for the pig for all three slides are going to be identical, right? So this is going to be same delta y, really, right? So no matter how you look at it, the delta y is going to be the same. So only thing weight's going to do is it's going to do the same delta y amount of work no matter which path it takes. We saw that from that, right? From the previous problem of this, right? The same thing, except this time we're just going down, okay? So, if you were to think about it, okay, work done on the pig is Fg dot delta y, right? So let's take a look. So work done, right, on pig by gravity is equal to, right, simply Fg dot delta y dot cosine, oops, no, let's not put that in there yet. So that is equal to, right, mg times delta y times cosine of 0 degrees. Okay? And that is pretty much same for all three slides. Okay? Because delta y is the same. This is not going to change. This is not going to change. All right? So you could say mg only does work, right, in the y direction. Oops, I'm running out of room, right? In the y direction. No work sideways. Okay. Well, what's going to happen to this pig's speed as it comes down to the bottom of the slide? Okay. Well, if we were to look at, right, work done is equal to change in kinetic energy, and since change in kinetic energy is equal to 1/2 mv final squared minus 1/2 mv initial squared, you know the initial is pretty much 0. So since work done is same for all three slides, the final velocity has to be, or final speed has to be all same. Okay? So therefore, same VF for each slide. Which one's going to be first, though? A, B, or C? Even though the speed is going to be the same for all three slides, which one's going to be the fastest? It'd be A, and and then B, and then C, right? It'd be the fastest here, right? So T sub A is less than T sub B, which is less than T sub C, okay? Because the pig's gonna reach the slide, the bottom here, the fastest. It's gonna reach this speed at here fastest, second fastest, third. All right. All right, let's take a look at number 13. All right, springs A and B are identical except that A is stiffer than B. So spring constant K, A is bigger than spring constant B. Which spring does more work if they are stretched? Okay. So if we were to think about spring, F spring is equal to Kx, or you could simply say negative Kx, but right now we're just looking for the magnitude, okay? So if you want to put negative Kx, that's fine, okay? So work done by spring is not same as F spring dot delta x. It is actually, we derived this together, I think. Right? So this is work done by spring. You cannot use the dot product on this. All right? So if it was stretched about same amount, so for part A, same x final means, right, work spring with bigger K, right, does more work. Okay? Why? Because it's going to be this, if your initial unstretched position is 0, then since it's going to be same amount of stretch, whatever the K value is greater is going to be the one that's going to do more work. Right? What about part B? By the same amount of force. Okay? So for part B, okay, same force, right? X final, right, is bigger for smaller K value, right? And, right, it is squared and the equation work is equal to negative 1/2 kx final squared. Right? So work spring is bigger for smaller K value. This is slightly counterintuitive actually for part B. Okay, so think it through. Now, obviously, they didn't give us exact amount of numbers and stuff, so you can't really check it. But make up some numbers and see if it works out. Okay. All right. Let's take a look at number 16. Does the power needed to raise a box onto a platform depend on how fast it is raised? Right. And the absolutely yes. Right. How fast means, right? I believe they're talking about time, not speed. But either way, I think it still means the same, right? So, since, well, first let's answer the question yes, right? Because, right, power is equal to the time rate of work done, right? Time rate of work done. So, if you think about it, right, work done is Fg dot delta y, right, over delta t, right? And so it does depend on time, obviously, right? Obviously. So if you want to even say, Fg dot v, because this itself is a v right here, right? So how fast? Yeah, it makes sense. Either way you look at it, it does depend on time, and it does depend on how fast. Okay. So if you were to do a smaller time, if you just go, it takes a lot more power than just go like that, which means, right, slower, right, as well when you're taking longer time. So yes, it does. Okay. So you could think of it as smaller the delta t, right, means bigger the power. Okay. So this itself can work for both ways, time as well as speed. Okay. Any questions so far? All right. Next. All right, work done by a constant force. A 55 kilogram woman climbs straight up a ladder 5 meters high, accelerating at 1.5 meters per second squared upwards as she climbs. Right? A. Calculate the work done by the woman as she climbs. Okay. Well, depending on how you look at it, I guess if she's just holding onto the ladder with her hands and pushes off of her feet, then the normal force, right, from the ladder to her is actually pushing her up. Okay. Or if she's actually pulling herself up using her hands and feet are just barely supporting, right, then it's F pull that's pulling her up. So depending on how you look at it or how you climb a ladder, it's just gonna make a different force that's working on her, right? However, the force that she needs to apply, whether to the ladder to create the normal force up, right, has to be minimum of her weight. Okay. Um, I don't know which one you guys want to use. You want to use F pull by her hand or F normal by her feet, right? So one way or the other, I think sometimes it makes more sense to have F normal going up, right? However, that F normal is actually going to be translated into F pull by her hands, right? So Let's do that. F pull. Okay. And that has to be minimum of her weight, Fg. Right? Okay. And of course, the delta y is basically in this direction, and that is 5 meters. Right. So we could start out by saying, right, sum of all forces is equal to ma, and then sum of all forces is equal to F pull, right, plus Fg, right? So we can simply say, right, Ma, well, why don't we just put it on here to save some room. So Ma is equal to F pull, I'm going to consider up direction positive. So F pull minus Fg, right? So let's solve for F pull to make her accelerate at that speed. So F pull is equal to, right, Ma plus Mg. And that is 55 times 1.5 plus 55 times 9.8. And if you work it out, you're going to get 621.5 newtons for the F pull. Okay? So that's how much she has to pull to climb at that acceleration. So for A, calculate the work done by women as she climbs. So for part A, right, work done by women is equal to F pull dot delta y. They're both in the same direction, right? So F pull times delta y times cosine of 0 degrees. F pull, delta y, same direction, 0 degrees. Therefore, F pull 621.5 times 5 times 1, because cosine of 0 is 1. And if you work it out, I think you'll get something like 3,107.5 joules. All right, what about part B? Part B asks, calculate the work done by gravity as she climbs. So work done by gravity is equal to Fg dot delta y. Now Fg is pointing down, delta y is pointing up. So it's really Fg times delta y times cosine of 180 degrees. Therefore, Fg, which is 55 times 9.8, right, times 5 times negative 1. Therefore, if you work that out, I think you'll get something like negative 2,695 joules for my work done by gravity. All right. All right. Number 2. A 650 Newton crate rests on the floor. how much work is required to move it at a constant speed, right? 3 meters along the floor if the coefficient of friction happens to be 0.2. So this is obviously mu sub k, right? So if you were to think about pushing it across the floor for part A, right? So for part A, I have F push and I have F friction. Right? Now F friction and F push has to be the same because it's going at a constant speed. Right? So if it's constant speed, then my acceleration is 0 and my net force is 0, right? So F push must equal to, right, F friction. Now, I'm not going to do this whole thing here because it's kind of obvious, right? So I'm not going to do that. So what is my F friction? F friction is mu times F normal. And since there's no other vertical force, my F normal is the weight, which is 650, right? So 0.2 times 650 is my, all right? So what's my F push in this case? That is equal to 130 newtons. All right? All right. So if this is true, the work done by push, right, is equal to F push dot delta x. Therefore, F push is 130 times delta x, which is 3, times cosine of 0 degrees. Right? So this thing comes out to 390 joules, and that's positive 390 joules. Okay? Now what about if you have to lift this thing vertically? For part B, since F push has to be up, right? And that has to be same as my FG. Right? So F push must equal to Fg in order to go at a constant velocity. If this is bigger, it's going to accelerate up, right? So work done by F push, right? Or F lift, it doesn't matter, same thing, right? So F push dot delta y. Now F push is going that way. My delta y is going that way. So again, it's 0 degrees, right? And here my delta x is going this way, so this is 0 degrees. So here, F push is 650 newtons times delta y of 3.0 times cosine of 0 degrees. Therefore, I get positive 1,950 joules as work done vertically. All right. All right, number 4. Oh, number 3. A car does 6 times 10 to the 4th joules of work in traveling 2 kilometers at a constant speed. What was the average force of friction. So I guess they're looking for the magnitude of this force, right? So oops. We know it's going to be in the negative direction, right? So when they say friction, it could be a lot of things. It could be a combination of friction between tire and the road, as well as the wind resistance and all the other right frictions involved, all you know combined together. Okay, so the friction obviously is going to be going in this direction, and then the force car is probably going to be going in this direction, right? Now, this force car obviously is the force of the engine in the car and so on, right? So if you were to add these two together, right, F car, right, plus negative friction, right, should equal to 0, right? Right, which is equal to ma, but there's no acceleration, right? So F car is equal to F friction. Okay. So let's see how much work was done by car. Then if we know how much work was done by car, then that's exactly how much work was done by friction. So let's see, work done by car, right, is equal to F car dot delta x. And F car is 6.0 times 10 to the 4th joules, right? Times 2 kilometers is 2,000 meters, right? Times cosine of 0 degrees. Oops, no, I'm sorry. F car is what we're looking for. This is what I wanted to say. Sorry. Sorry, that's what I meant. So let's solve for F car. If we solve for force of car, then it comes out to, I guess, 30 newtons, right? So since F car is equal to 30 newtons, then F friction must also equal to 30 newtons. Okay? All right. Moving on. So, number 4, how far must 200-kilogram pile driver fall if it is to be capable of doing 13,000 joules of work? Okay? All right. So, you're just letting it fall into this, right? Rather than, if you ever see like those people, building houses near the shore, they're driving down these huge like telephone poles inside the sand to build this right pylons, and they use these pile drivers to pound these huge telephone poles inside the sand. All right, so they just letting it lift it up, and they're just letting it fall on it, right? So the work is really done by the gravity. Okay, so if we were to say work done, right, by gravity, right? So here, this is delta y, right? And this is Fg, right? So work done by gravity is Fg, right, dot delta y, right? So you know Fg is going down this way and delta y is also going down this way, so you know the angle between them is 0 degrees. So here we have mg times delta y, right, times cosine of 0 degrees. So this here is work done, right? So we have 13,000 joules is equal to, right, 200 times 9.8 times delta y times 1. So delta y is equal to 6.63 meters. All right. Number 5. We have 2 kilogram object is given a displacement of this much along a straight line. During the displacement, constant force of this much newtons is being applied, right? So I don't like how they put all these newtons inside each one of those components as well as these meters. So it looks so intimidating. All right. So find the work done by the force for this displacement. All right, so work is equal to F dot delta S in our case, right? So force happens to be, right, 2x hat minus 1y hat plus 1z hat dot delta S is, I'm going to change the color so you can make a little bit of difference here. All right, 3x hat plus 3y hat minus 2z hat, right? All right, I hope you guys remember the dot product, right? So F dot delta S gives you, right, Fx Sx plus Fy Sy plus Fz Sz is the dot product for Cartesian form, right? Therefore, if you were to look at this, right, I got 2 times 3 plus negative 1 times 3, right, plus 1 times negative 2, right? No x hats, no y hats, no z hats. Okay? So here, when I work this thing out, I get 6 minus 3 minus 2, and I get 1 joule. So that's part A. All right, find the component of the force in direction of displacement. Whoa, what the hell do they mean by that? So here, if you were to look at this in three-dimensional thing, it's kind of hard to imagine, but it's going to be in the first quadrant with below the XY plane, right? So if you were to look at this in a crazy three-dimensional space, so here, let's say this is your X, this is your Y, and this is your positive Z axis, okay? And this is your negative X, and negative Y, and negative Z. Your delta S happens to be in the first quadrant, like 45 degrees this way, right? Positive X 3, positive Y 3, and then negative 2. So it's down here somewhere. So it's like this is your delta S. Oops. Can't even use the ruler properly here. So that's my delta S. Now my force is in second quadrant above the XY plane. So it's like negative, not second quadrant, it's actually in fourth quadrant, like positive 2, negative 1, and positive 1. So my force vector is like way out there in a space. It's kind of hard to visualize, right? That's my force. They want to know how much of this, if I were to like cast a shadow of my force vector onto my delta S, what is this, right? So this force in S hat, basically. Not, right? So they want to know what this is. Okay? So how do we solve for that? Okay? So this right here is the right angle because I am casting a shadow onto my S. This angle here is angle between F and delta S. Okay? So if I were to redraw this from this view, let's say I'm looking at it from here, like here. So I am looking at it like this, right? This will be in a plane, right? This will be in a plane where I would have my here's my delta S, and here's my force, right? Now I'm looking at this at like flat plane, and this is the angle between F and delta S. Oops, why did I put that vector notation on that thing? So, how do I calculate this angle? Because if I were to cast this shadow straight down, right? So if this is what I'm looking for right here. And this is 90 degrees. From here to here is 90 degrees. Okay? So first I need to figure out what this is. So I'm looking for F, right? S hat. So S hat is now the axis now. All right. Ready? Here we go. All right. So since work, we already said work is equal to not only this, right? That is also equal to the magnitude of the force times the magnitude of delta S times the cosine of the theta between F and delta S. We already know that this is 1. We already calculated that. And that is equal to, what is the magnitude of my force vector? My magnitude of my force vector is equal to square root of, right? 2 squared plus 1 squared plus 1 squared, which is equal to radical 6. And the magnitude of my delta S is equal to square root of 3 squared plus 3 squared plus 2 squared. And that is square root of 9 plus 9 plus 4, which is 22. Okay, so here I have radical 6 times radical 22 times cosine of theta between F and delta S. So theta between F and delta S is equal to 1 over the product of these two, right? So radical 6 times radical 22. Oops, I forgot the cosine. So what is theta? That is cosine inverse of all this mess, okay? And that, if you work it out, comes out to be 85 degrees. So the angle between the force and delta S in its planar view is 85 degrees. Therefore, the cosine of 85 times the force F represents this F S hat. Okay? So F, we know it to be radical 6 times cosine of 85 degrees. So my F in the delta S axis direction happens to be, right, 0.213 newtons S hat. So it's along the displacement vector axis. All right, any questions? All righty. Let's take a look at the next problem. All right, so these are exercises. So here, motion in one dimension with constant force. Okay, so 45 kilogram block of ice slides down a frictionless incline 1.5 meters long and 0.91 meters high. Right? So worker pushes up on ice parallel to the incline so that ice slides down at a constant speed. Okay, so the man is pushing this thing upwards and ice is sliding downwards and delta x is downwards and FGX is downwards, right? But the net force in the x direction should equal to 0 because it's coming down at a constant speed. Okay? Okay? So, find A, the force exerted by the worker, and find the work done on the block of ice by the worker, and the weight of the block, and the normal force exerted by the surface on the incline on the block. Okay? So we got to find all these forces, huh? All right, let's do that then. So here, ice will have its Fg straight down, obviously. We don't know the angle yet, but I'm sure we can figure this angle out because they give us the dimensions of this incline, right? So this angle here is theta, obviously. So here, this Fg will be broken up into its components of, right, Fgx and Fgy. So this is Fgx, and this is Fgy, and this is Fg, and this is the normal force going straight up from here. Now, since there's ice happening, I'm going to assume there's no friction, right? Now, the force applied is actually going up this way. The force push, right? F push by the worker. Right? And the delta x is actually down the incline like this. That's not a force vector, that's the displacement vector, so don't get that confused in there. Okay? All right then. Let's figure out what the angle theta is. Because it looks like from here, right, this incline itself is 1.5 meters along the incline. So 1.5 meters this way. And the height itself is 0.91, right? So we could probably figure out what this angle theta is. Okay? So since sine of theta is equal to 0.91 over 1.5, or theta is equal to sine inverse of that, right? So my theta comes out to 37 degrees. So that's good to know. My theta is equal to 37 degrees. That means this is also 37 degrees. All right? All right. So how much is force push? Well, we know, right? Force push, sum of all force in the x direction is equal to max. And you know, sum of all forces in the x direction is equal to, right, Fgx plus F push, right? So since max is equal to, I'm going to consider the downward direction as positive direction, okay? So just going to consider that to be my positive direction. So my Fgx is positive minus F push. Right? Acceleration is 0. And this is mg sine theta minus F push. So my F push is equal to, right, 45 times 9.8 times sine of 37 degrees. That comes out to 265 newtons for my F push. All right. So how much work is being done, right, by F push? Well, work done by F push is equal to F push dot delta X. Therefore, F push is, well, that same thing as saying F push times delta X times cosine of, well, F push is going this way, delta X is going that way, that's 180 degrees, okay? So this is negative 1, so negative 265 times 1.5, right, meters, and that is negative 398 joules of work done by F push. All right, what about part C? Weight of the block. Now we're looking at how much work is being done by Fg. Well, there's two ways to look at this. You could say Fg dot delta X is one way of looking at it. Or simply, this FGX is the only component of my Fg doing work on that. Let's do it both ways just to show you that it works out both ways. Okay? So if we were to look at work done by gravity, it is simply Fg dot delta X. That is simply mg times delta X times cosine of, what is this angle right here? That angle is 53 degrees. Okay? Therefore, if I work that out, the mass, which is 45 times 9.8 times 1.5 times cosine of 53 degrees. So what is that, John? Well, here's 45 times 9.8 times cosine of 53. I get, I forgot to multiply by 1.5 times by 1.5. All right, I get something like 398.1 joules. Well, let's see what happens if I were to do FGX dot delta X. Right, so this is one way of doing it. if I were to do it this way, then my FGX is mg sine of 37 degrees times 1.5 times cosine of 0 degrees, because FG and delta x are in the same direction, so 0 degrees. So let's see what happens, right? So 45 times 9.8 times sine of 37 degrees times, right, 1.5 times cosine of 0, which is 1. All right? So here I got 45 times 9.8 times sine of 37, right, times 1.5. Look at that, I get the exact same value. Okay? Get the exact same value. So I get 398.1 joules. So hopefully you can see, you could work it either way, and you'll still get the exact same answer for C. Okay? All right, so what about part D? Work done by the normal force. We should know what the answer is on this. Come on. Right? That is equal to, right, mg cosine theta times delta x times cosine of 90 degrees. And you know cosine of 90 is 0. Therefore, this whole term goes to 0. No, don't do that. Don't do that. That's not cool. All right. And then, what about E? The resultant, or the net force. Well, since my net force in the x direction is 0, and since my net force in the y direction is 0, my net force in total is 0. So for part E, work done by the net force is equal to the net force dot delta x. The net force in x is obviously 0 because it's going at a constant speed, right? No, don't do that. Don't do that. Don't do that. All right. Voilà. Hein? Nous avons fini. Oui? Oui. All right. So I think I'm going to just stop here. Hopefully you should be able to continue on and finish the rest of this homework packet as we move on. Most likely, I'll try to finish it up by Friday, and then we'll do assessment on during the weekend, I guess. So try to really get this thing out of the way, and you need to practice on your own. You cannot be just watching me do it, you know, because when you watch me do it, it's going to make perfect sense to you, because I usually do them correctly. And when you see someone do it correctly, it's going to make perfect sense. But you need to learn how to do it on your own first, right? So try to struggle through it first rather than just watch me do it, right? It's like watching Michael Jordan doing free throws, you know? When you watch Michael Jordan do free throws, it looks easy because he does it great, because he practices like 1,000 times a day. But when you try to go out there and do free throws, it's kind of difficult. Anyway, same thing. All right, I'll stop here.